Now I'm so out of shape that would probably just murder me. I used to ride up Immigration Canyon every Saturday morning. Mill Creek Canyon. Yeah, pretty good. All right, so as of last Wednesday, we were talking about power amplifiers. And one of the things that we were noting about the power amplifier that's a bit different than the LNA is, it's working in the opposite direction. So the power amplifier is not receiving a signal from the antenna, it's driving a signal into the antenna. And because of that, it has to work into a widely varying range of impedances. So the antenna nominally is designed like all other RF components. Typically, it will have a characteristic impedance that is designed to be 50 ohms. But unlike other components, the characteristic impedance or the input impedance of the antenna will vary as you move around in the environment. We talked a little bit about this. So I'm walking next to a glass and metal building. The impedance is going to be affected by the glass and metal building. If I'm in the middle of the drill field, it's probably going to be pretty close to normal. If I'm holding it up to my head or have it in my pocket, talking on a Bluetooth, impedance is going to change. In the old days, they said that it had to be able to withstand a 10 to 1 VISWAR. Now, most PAs are tested more like 4 to 1. You might have to survive a bigger range, but they're only expected to work into maybe a 4 to 1 VISWAR. Okay, different than an LNA also is, the LNA, we assume that it's a small signal circuit. We did talk about IP3, so we do talk about linearity with an LNA. And indeed, we expect our low noise amplifiers to work with wide signal swings. So they are large signal, but PAs are inherently large signal. We're going to be trying to drive them with high power into an antenna, and it turns out that they're more efficient the closer we can keep the PA to its saturated output power. So a couple of things that we need to do, though. So our assumptions are not going to ride around this small signal base anymore. Now, when we do the initial analysis, we're going to do it assuming that we have sine waves going through the amplifier, but the amplifier is going to be a large signal. It's going to be a large signal being processed through it, and that means that the wave is going to be distorted, compressed. It's going to change its shape. When the distortion occurs, you can expect that the bias point will move. So as the wave gets clipped, say, on one end, it would change the average value of the waveform, and that's going to create a change in the DC level. When the DC level changes, the DC level moves. Now all of the calculations that we made, remember the gain is something like GM times the load resistance. Now that's out the window. Our simulations that we're going to use are going to be modified to accommodate this change in the signal level performance of the amplifier. So when we were looking at matching networks, and even when we started to look at noise figure, you can simulate noise figure for an LNA using a small signal simulation, something that's tantamount to an S parameter simulation. Those are all small signal simulations. When we start to do PAs, we're going to use a different set of tools. Our tools will be transient based. So this means we're going to look at the time domain waveform. And we have a couple of other tools that we will use. One is called periodic steady state. If you open up Cadence and look in your simulator, you'll see a tool called PSS, that's periodic steady state. What PSS is basically a transient simulation that will simulate exactly one period of the input waveform, and it will it will actually simulate a couple of periods. Once it finds periodicity, then it will project that periodicity continues forever, and it will look at just that last period that it simulates once it's found the periodicity, and it will do analysis on that particular waveform. That waveform can include distortion or nonlinear effects as long as it's periodic. And then the other tool that we might employ is called harmonic balance. And harmonic balance is a frequency domain large signal simulator that basically employs the principle of a Fourier transform. If I can represent a time domain waveform as a sum of sinusoids with different harmonics, then I can do so in a frequency domain based simulation space. So I can basically take all the large signal waveforms and represent them as a sum of different harmonics. That's what harmonic balance is going to do. Now, when we simulate IIP3 for low noise amplifiers, we can use the PSS tools. I'm actually going to try and show you how to use those either today or Wednesday. If not, I'll show you in the video. So when we're doing the large signal side of the LNA, we want to estimate its compression point or its IIP3. We use these transient based tools. If we're just simulating the low, the small signal side, noise figure, gain, we can use the small signal tools, S parameters, AC analysis, and so on. All right, so let's look at our amplifier characteristics. We've talked about this before, but when we have an ideal amplifier, we expect that its performance is going to look something like this. We just expect that the output is going to be proportional to the input. And ideally, for every 1 dB of input power that I input into the amplifier, I'll get 1 dB more of output power. So if I put in some input signal PI, and then I put another input signal in PI plus 1 dB, then I expect that the output P out changes to P out plus 1 dB. There might be an offset in the curve. The offset in the curve, assuming that this is the origin, the offset in the curve from the origin is the gain of the amplifier. Okay. Now, in an ideal amplifier, what we're really saying is that the output power P out in dBm is equal to Pn in dBm plus the gain in dB. As input is increased or decreased, the output changes by the same proportion. Okay. Now, what happens with a real amplifier? Well, a real amplifier, when we get to high values of output power, starts to deviate. So for small signals, the real amplifier's gain is linear and it's going up dB for dB. But as we get to high values of output power, it will start to compress. And as the waveform compresses, that means that we're delivering less power into our fundamental. And so the output power is going to saturate. All right, so we almost never can actually measure saturation, but we should see some type of saturation behavior where the output power just stops decreasing or stops increasing at all. Yeah.
What do you say is putting less power into the fundamentals? I mean,
well, what I mean is ultimately, ideally, what's happening is every dB that we add into the input signal tone, we're getting a dB more out at the output. But what's going to happen as you start to as you keep increasing the input power is that you're going to create a voltage or current waveform at the output that starts to distort.
Okay, I got you. So
and as it distorts, that means that you're adding you're taking power that would have gone into the fundamental frequency and you're transferring it into other harmonics.
Why can't you measure it? Is it just, I guess,
it just means, ultimately, I guess what I mean by you can't measure saturation is at some point you can just keep driving power and you just don't see any increase. But you might still be able to keep driving more power in. You're probably never going to get to a point where you get 0 dB increase in the output before you blow your amplifier up. Yeah. Yeah, but it'll saturate enough that you'll be able to tell that you're well compressed. All right, so a real amplifier tends to saturate when power reaches its limit. It's different for every amplifier. So what are things that cause, why do you think that you reach a saturation point? What causes the amplifier to saturate?
The limit of current based on your device size.
Yeah, so the current driving capability of the device is dependent upon how big the device is. Yeah. What else? Well, let's assume that the load is fixed. It's just a 50 ohm resistor. It's not changing. So we have a perfect antenna that's always staying 50 ohms.
The voltage swing is limited too.
Yeah, the voltage swing gets limited also. So you have a finite supply, and that means that and for any real amplifier, that's going to limit the voltage swing. The width of the device is more or less going to limit the current swing. Both of those things are going to limit the output power. One thing that we don't necessarily always talk about is we talk about small signals. So you think as you keep driving the input power smaller, well, it just stays linear. A lot of real amplifiers will even deviate at smaller levels as well. Probably not as dramatically as I've drawn it there, but you'll see some deviation. Yeah.
So we care about the linearity of this line graph that we have. And P equals L, right?
Yeah.
But does it matter how much the slope of that, or?
The slope of that should be just dB for dB.
If it becomes, the slope becomes 2 instead of 1, does it have any specific meaning?
Well, I mean, that would imply that instead of saturating, the amplifier was doing something like that, right? That type of behavior would imply that we're somehow adding energy into the system from somewhere else.
I'm not talking about the saturation part, just the line, the straight line. If it goes from 1-to-1 mapping, if it goes from 1 to 2 mapping, for example, if I add 1 dB, it increases 2 dB. Does it matter, or it can be 1 dB?
There's no way that a real amplifier can do that.
It could be like I add 1 dB and then the output goes up half dB. That would be like you have a large loss.
Yeah, I mean, there can be other, so
that-
there can be other things, but the amplifier itself, I expect the slope to be 1 dB for 1 dB. So this slope for a real, this slope. Oh, I see what's happening. This slope should be 1 dB for 1 dB.
Can you calculate the efficiency of the amplifier by the slope and how much that is like below that?
No. Remember, so the gain of the amplifier is the offset, you know, of the curve, right? So this offset is the gain of the amplifier, but no, ideally, no matter what happens, I put 1 dB more power in, I get 1 dB more power out.
What if there's like a loss at the fundamental frequency?
If there's a loss, that's just going to change. So if there's a loss, that changes the relative position. It changes the offset of the line, right? Yeah. But still, 1 dB input should yield 1 dB more input should yield 1 dB more output, even if there's a loss.
Well, if you find a device that does 1 to 2, then
Well, there are ways. There are like multipliers. I'm talking about linear amplifiers that should be that way. There are things that I can do that will double that will have a slope that's 2. But for a linear amplifier, I want it to have 1 dB. 1 dB increase in input power gets 1 dB increase in output power. Okay, so yeah, we do have nonlinear circuits that will, that we can use, but we're assuming a linear circuit. These compressions at low power tend to have something to do with, limitations in the device linearity in the device. Okay. Now I know that we've said it before. We've talked about dBm when we were looking at low LNAs also, but dBm is just decibels relative to 1 milliwatt. So it's 10 log 10 of the power in milliwatts. 30 dBm is 1 watt, 1,000 milliwatts. Okay, so let's zoom in on this distortion in the amplifier. So we're going to examine kind of the peak portion of the curve, and I'm going to draw it a little bit more carefully. So let's assume that we have, some deviation that's starting to happen in our amplifier. The point where the curve saturates, we're going to call PSAT. Oftentimes, we'll just define this as when the saturated output power is some fixed level below where it should be. So, for instance, because it's hard to always drive these things fully into saturation, oftentimes we'll find when the peak curve is, say, 5 dBs below the ideal curve, and we'll say that it's saturated, or at P5 dB. A more common measurement in terms of linearity is a point where there is a 1 dB deviation between the two curves. So the output power from the actual amplifier is 1 dB below the output power, the ideal output power. And they call this point P1 dB. So we can have P out 1 dB, or we could reference it to the input. So this is the output power level. P out 1 dB is the output power level where the curve is exactly 1 dB below where it would be if it were an ideal amplifier. All right, so our P1 dB is power level. All right. Now, generally, we're going to operate, we consider an amplifier linear when it's operating below its P1 dB point. Now, in many cases, we actually have to operate it at a power back-off level that is actually much less than P1 dB, depending upon the signal that we're looking at. So I just noted more on linearity in a little bit. We're going to talk about what are the impacts of linearity, the power amplifier. The first thing that we're going to talk about, what's the most important thing about a power amplifier? Efficiency. Efficiency, I might argue also output power. Whatever its peak output power is, but certainly no matter what, we don't want to waste energy, so we're going to talk about efficiency. All right, so efficiency we're going to define as how much usable energy do we get out of the amplifier relative to what we put in. And we have a couple of different metrics for efficiency. So let's talk about the first one. So the first one we call drain efficiency. As you're starting to read some of your papers, many of you are looking at power amplifiers. They denote it with the Greek letter eta. And this is equal to P out divided by PDC of the drain. So just the DC power consumed by the drain of the transistor, or the collector if we were looking at a BJT. But all right. So in a linear amplifier, there is always going to be some DC current that's flowing through the device, IDC, and we're going to deliver some AC power into our output. Let's get rid of this dark blue. Fuchsia, the future.
I can't even see it out there. Just looks like that.
Well, here, it's vibrant. The screen is bursting with color. Sorry. You can come experience it if you want.
At the end of us.
Okay. All right. So here, what we're measuring with drain efficiency is that the transistor dissipates power due to the average DC current running through it. Okay. All right, this is the bias current that's flowing through the device. Now, drain efficiency is a good metric for evaluating the impacts of a load network or the bias condition of an amplifier. So if I take an amplifier, the same power transistor, say, and I just want to see what happens if I put a different load network on it, or I bias it with a slightly different DC condition. Drain efficiency is good to do an apples to apples comparison of, how is that bias condition affecting how much power the transistor consumes. The power stage is going to consume the most amount of power, ideally, in the circuit. So it's also going to tell us a little bit about what we can expect for the total power consumption from our transmitter. But we also have to drive the thing, and drain efficiency does not include that. So ultimately, what we're saying is that the drain efficiency doesn't measure the impacts of the input side of the amplifier, just what we do with the DC operating point and load. If we want to measure the input side of the device, we have another metric. We'll label this one power added efficiency. In your texts and in your papers, you'll see this sometimes called PAE. PAE is equal to P out minus Pin over PDC at the drain. All right, so ultimately now we're adding some factor that takes into account what's going on the input side. So really this is taking into account the fact that the PA has finite gain. If you assume that we're measuring P out in dB minus Pn in dB is the gain of the amplifier. I should also note that we have to be careful what units we do this in as well.
Yeah, sorry. So those are all dB units. No, they're dividing, so it has to
These would be linear because we're doing, yeah.
I'm gonna say.
Yeah. You could do it in dB, then convert to linear and then divide. Yeah. Okay. So this metric is a bit more complete, but it doesn't take into account what happens if the gain is low. In fact, what happens, what would we say the PAE is if the input power were more than the output power?
Negative PAE.
Yeah, we'd have negative PAE. So it's not, you're right, it's not an amplifier, but theoretically we should be able to measure the efficiency of any network. This would imply a negative PAE, which doesn't necessarily make any sense. So if we have low gain systems, I like to use what's called the total efficiency. We'll call the total efficiency. Total efficiency deserves fuchsia. I know we can't see it, but it deserves it. Total efficiency, we're just going to change things around a little bit. It'll be P out divided by PDC at the drain plus PN. So here it doesn't really matter if we have low gain or not. If the gain is if the gain is big, 10 dBs or more, PAE and total efficiency are approximately equal to one another. But if the gain is small, these two will start to diverge. The one thing is that total efficiency will never be negative. So I think it's a more complete metric. Really what we're doing ultimately is just accounting for everything that's bad that we don't want in the denominator, everything that's good in the numerator. All right, so the next thing that we'll look at is linearity. All right, so in an RF system, a PA must not distort the signal. Distortion causes a lot of problems. What are some of the problems? Well, unwanted emissions. When we distort our waveform, definitely doesn't deserve fuchsia. These are bad. All right, so the first problem that we're going to have from distortion is unwanted emissions. So, you can imagine as you start to clip a sine wave, for instance, that you're going to start to create harmonics at different frequencies. So if you just do some basic Fourier analysis on that clipped sine wave, you're going to start pushing energy into those into different harmonics of the wave. So you're going to get harmonic distortion. Due to compression. This is where we're going to see the clipping waveforms, things like that. Now, we're always going to try and drive our PA up, to the level where it's going to start to clip. That's where it's most efficient. But we'll have to measure how much it's clipping, and we'll measure how much, how much signal we're bleeding into those tones. Because when we make a transmitter in the US, the laws of how we use that transmitter are governed by the FCC. The transmitter is an intentional radiator, and there will be limits on how much power you can radiate into unintended bands. You're only allowed to radiate a certain amount of power into the band that you want to radiate in. Anything else is affecting somebody else's radio system, and it's regulated. All right. Ultimately, if we put enough distortion into the signal, we're going to misshape our tone to the point where we can't demodulate it at the receiver. The tone won't be recognizable anymore as it comes into the receiver. All right, and if we're using very complicated waveforms, it doesn't take very much distortion to make it to where even though you might be able to see the general shape of the wave, just little distortions in the tiny imperfections cause it to where you miss a bit or a couple of bits. And if you're doing that regularly, then you're getting to the point where you can't recover the signal enough. Your packet error rate goes too high, for instance. And then the last element will be that out of band noise is going to be raised. So any distortion, generally causes just the whole noise floor of the system to rise. And the reason for this is we're not just putting a single tone into our system. We're putting modulated tones through the system that are spreading the energy across some band of frequency. That energy that gets spread when it's bled into the distortion tones, it doesn't have a single tone shape. It's got the shape of the modulation as well. And so I raise the entire noise floor of my system out of band. If I, and of course, depending upon how distorted you are, that gets worse. I'm going to abbreviate out of band to OOB. So one thing that can also happen because we have, if we're driving the PA into a nonlinear regime, is it can have nonlinearities that cause the out of band noise to fold back in band, where the noise from out of band is also adding to the noise in band and degrading the signal to noise ratio even further. All right. So we talked about modulation a little bit when we were looking at the receivers. Generally, almost every radio system nowadays uses some form of amplitude and phase modulation. And our example is the 16 QAM constellation. All right, so there's our 16 QAM constellation. And we're embedding, what we're doing with that 16 QAM constellation is every point, there are 16 points, can represent 4 bits at a time, right? Okay, so every 4 bits in that constellation has a unique amplitude and phase. They don't all have unique amplitudes. They don't have unique phases. They have a unique amplitude and phase in this particular case. All right, so what happens to this constellation if a signal is distorted? So ideally, when we send our signal through the amplifier, a transmitted point would land exactly inside of the, inside of the ideal circle here. So ideally, our output is perfectly in line with what we expect. Now we're going to see a couple of types of distortion. I showed you earlier amplitude distortions. So, the deviation of our non-ideal amplifier from our ideal amplifier in terms of amplitude is called AM to AM distortion. You can imagine that this is problematic because if I looked at that constellation on the prior page, I have some points in the constellation that are closer to the origin, so they have low power. Some points in the constellation that are further away from the origin, so they have higher power. And if I have this amplitude to amplitude distortion or AM to AM distortion, I'm going to, as my input power changes, I'm going to get a time varying output change. Ideally, it would be proportional. In reality, I get less gain for that high power point than I should because of the compressive behavior, and that causes distortion. Now, the other thing that we might find is that the amplitude, the phase, the way that this is really showing up, the curve, the red curve is the real output power. The green curve is the ideal output power. So ideally, for any linear amplifier, the gain is flat for all input power. So the figure on the right is what our ideal gain should look like. In reality, what's happening is our red curve here, the gain is saturating, is deviating. And the delta here is due to compression. The delta between that ideal gain curve and the measured gain curve is what we measure as our AM to AM. Okay, well, it stands to reason for an amplifier that if we have AM to AM, we might also have AM to PM. So the amplifier also has a phase response, a phase at the output of the amplifier as the input power is increased. Ideally, we want the phase of the output to stay constant, no matter what the input is. Why might the phase of the amplifier change with respect to power?
Each level of power can affect the transistor operating point. That one, because when we write the GM of the transistor as a Fourier transform, each power of that Fourier transform will have double and triple of the phase, so it can affect it.
So that's correct that the linear GM characteristic might have some nonlinear terms in it, but there's something that's much more dominant in terms of the phase response. It does have to do with the DC change. Think about an amplifier. So a small signal amplifier, we say typically has an output pole, right? And the pole is due to the R's and C's. Well, For a real amplifier, as the bias changes, as the bias point changes on the amplifier, the cap changes. Remember, the caps are depletion mode caps. As the depletion region expands or contracts, we get different amounts of caps that are power dependent. So indeed, what we see might look something like this. Now I'm going to draw the AM to PM so that you have a lot of change at high power. Depending upon the class of amplifier that you're looking at, the distortion characteristic might shift to where you're more distorted at low power for the phase shift. Just depends upon the class of the amplifier. But the key point is that there's a deviation between the ideally flat phase with respect to input power and the real measured phase.
Dr. Walling, quick question, just to clarify.
Sure.
Is it purely because the parasitics are changing because of bias point? That's the main
what
reason?
Vedad mentioned is correct. Technically, as the bias point changes, that we treat the GM characteristic of the device as if it's a constant, but in reality, the GM of the device is going to change as a function of bias point as well. So that will have some impact. But the dominant impact on AM to PM response is the fact that the RC time constant is changing, and the C is changing primarily because of the bias point.
Okay, and that would be the C's would not be the intentional C's that we place. That would primarily be the parasitic C's.
Well, it can be the intentional C's that we place. So we only showed you one type of capacitor the other, or two types of capacitors the other day. One was a MOM cap or a VN cap, and the other one was a MIM cap. Those ones are fairly linear because they're really just dependent upon the metal insulator metal overlap area. But let's say you decided to use a device capacitor in your network, which wouldn't necessarily be a good choice, but it could be done. Then that device capacitor, a MOS capacitor, would have a dependence upon the power level.
Got it. Okay.
Okay, so just noting that the input power modulates the internal device capacitance, and that causes a phase shift. Now, the other thing to note is that we're trying to capture a lot of nonlinearity here with really hand-wavy first-order description terms, right? RC time constants and things like that. What's really going on, if I look at the device model, is there are all kinds of things that are very dependent upon the bias point of the device, and all of those things start to play a role in this. And so if you want to really understand distortion, you have to do things like take a Volterra series analysis of the transistor. And really that's just a model of all the effects of the device. What does this look like on our constellation? Well, you can imagine that for AM to AM, we had this nice ideally you can pretend this is a completely symmetric square. And now maybe at low power, I have a pretty good linearity. So my signals at low power are landing more or less where I expect them to land. But as I go to higher power, they're landing further and further away from their expected value. All right, so that's kind of what an AM to AM distortion is going to look like. Is it's going to kind of, as the power is increased, it'll compress the constellation. At low power, might look good. At high power, it gets compressed. What does an AM to PM distortion look like? What do you think an AM to PM distortion might do? Yeah, the phase changes as a function of amplitude. So again, yeah, it's going to kind of maybe pinwheel or something like, yeah, maybe spiral is a better term. Here we'll draw it and you can determine. All right, so again, at low power, the signal, lands more or less where I expect it. But as the power is increased, I get a bigger proportional rotation. So these corner points are the highest power points, right? So they're going to rotate far away. These other 2 points, they have higher power than the low power points, but maybe I get a slightly smaller shift. It's causing everything to kind of rotate. Okay, now almost every amplifier has some combination of these two distortions. So we don't just get amplitude distortion and phase distortion, we get both. So our points are not only compressing in, they're also rotating. Our job is to make the amplifier as linear as possible and prevent that for as wide a range of input power as possible. If our amplifier is good, it achieves almost no distortion up to a very high power level. All right. So just to summarize, what we're really showing here is that, the amplifier with compressing gain, as power is increased,
These graphs are just the same as the other page.
yeah, just the same as the other page. So for AM to PM, what we're saying is that the phase is rotated differently at different power levels. Now, I showed you a case where it's rotating more at high power levels, but it can often happen the opposite way around, where it rotates less at higher power levels and more at low power levels. Just depends upon the device, the mode of amplification that we're using. All right, so I noted that we can have a couple of things here. These are more rare. We can also have PM to AM distortion. Very uncommon to see PM to AM distortion, but it can happen. Maybe a bit more common to see PM to PM distortion. So those are two special cases. But almost always, real linear amplifiers are dominated by AM to PM and AM to AM. Okay, so for our spurious distortions, if we have these non-linearities, we put in some signal at our input. Ideally, we get that signal at our output. In reality, we're also going to get some tone at 2FO. It shouldn't have almost the same amplitude as the input tone. And at 3FO, and so on and so forth, we go out here to NFO. We're still going to be getting something out here. Okay. Now, the one thing that I'll say is typically, as with harmonic distortion, it's decreasing as the harmonic goes up, but there are some cases that can cause that not to be true. If we're using a differential amplifier, we tend to suppress even order harmonics. We talked about that the other day. Same is true for a power amplifier. And then sometimes just the shape of the network causes the some harmonic tends to be cancel better than others. In which case, we wouldn't see, or we can see that the amplitude of the tones is not always decreasing as the harmonic number is increased. All right, so that's kind of a general overview of what's really different about a power amplifier, what we think about with a power amplifier. Everybody comfortable that they understand our language for describing a power amplifier? All right, well, let's start designing a power amplifier. All right, what's really different about a power amplifier compared to a low noise amplifier? These circuits look pretty identical, huh? So when we design an amplifier, really, we're going to have some type of transistor. It could be a power transistor or a low noise transistor, but it's going to be doing, it's doing the damage. It's creating a proportional current that's going to be run into a network that will, create some proportional voltage. Ultimately, we equate that to some type of power gain. What's really different in terms of the design philosophy of the two is, well, I will definitely choose a different bias point for the LNA than I will for the PA, and that bias point will have to do with the noise. And if we get time, what I'm going to do is show you that a low noise amplifier's noise is minimized when you optimize the current density through the device. So that's it's definitely something that's different. Ultimately, what we're going to show in just a few moments is that this matching network, when I look into it, what I want to do looking into the matching network is make the load that I present to the PA equal to some optimum termination resistance. Now, the device itself might have some parasitic capacitance. In fact, it always will have some parasitic capacitance. So there's some drain capacitance at the device. But I can do things like try and, I can resonate my drain inductance with my drain capacitance. And then I'm going to design a matching network that's going to be designed to transform 50 ohms to an optimum termination resistance. That's going to have to do with the load line. We'll look at that in just a moment. Okay. So we're going to do what's called a power match, and this is going to be to maximize power generation. Now, this is different than our LNA. Remember, when we look at our LNA, we might have considered that the impedance looking into the LNA is equal to some RD minus J omega CD. And my matching strategy here was to make my load impedance equal to RD plus J omega CD, the complex conjugate. So this is a conjugate match, and the purpose of this match is to maximize gain or power transfer. Okay, these two things sound similar. Maximize power generation, maximize power transfer. What's different? The power match is presenting an impedance that allows the transistor to generate the most amount of power that it can possibly generate, whereas the power transfer match is allowing any power that is generated by the device to be transferred to the output. Subtle difference, but they are very different. All right, so let's go to our load line for the amplifier. So hopefully we remember load lines from some circuits course in the past. All right, so our drain current is proportional to the drain to source voltage. and also to the gate to source voltage. And we get these different family of curves for different gate to source voltages. Now, no matter what, every device that I use has some maximum drain current. I'm going to call that ID max. This is going to have to do with the total width of the device. If I make a device wider, it will have more current driving capability. It'll have a higher ID max. If I make the device narrower, it will have a lower ID max. And then every device is also going to have some VD max. Now, in a MOS device, the VD max has to do with when the device breaks down. So, for instance, for every process that you use, there will be a VDD for the process. VDD for the 22 nanometer process. What's VDD for the 22 nanometer process? 0.9. Yeah. That generally has to do with, well, it has something to do with the oxide thickness. It's not the critical E field, but it has something to do with that. Okay. Now, what I want to do is devise a scheme where I can cause the transistor to be able to swing all the way through its maximum voltage range and its maximum current range. So we're going to say that the maximum voltage will start at VD max, and I need to keep the device acting as a current source. So I'm going to have, you know, a region where the device is in saturation. So ideally, I want to swing from the point where the device enters into saturation all the way up to the maximum voltage, VD max. And this is called a load line. Okay. And the slope of this line is something like -1 over RL. Okay, so the slope of that line is going to dictate the voltage swing and current swing at the drain of the transistor. Now, we might be, you know, one other thing to point, we might be biasing this device into different regions. So we might be using different, you know, VGSs and VDSs. So we still have the same concept of a quiescent point. We're going to design this to operate around some bias point or some Q point. More on that in a minute. That's going to determine the mode of operation that we're in. So you might have heard of a class A amplifier or a class B amplifier. The quiescent point is going to determine the mode. The load is going to determine what our power swing is, or, you know, what our maximum power potential is from the device. All right. So ideally, we want, when we're making a power amplifier, we want to pick a load that allows us to swing through the maximum possible current range and the maximum possible voltage range. All right, so we already highlighted this. Now, one thing I didn't throw on the last slide, this point at the low end, sometimes we call the knee voltage of the transistor. So you'll see in PA papers sometimes this is called V knee. We have our VD max and our ideal load line went through like that. Okay, so what this tells us is that the optimum termination resistance for a device is equal to VD max minus V knee over ID max. Okay, so we get full voltage and current swing there. Now what happens if our slope doesn't exactly match this? So for instance, what happens if our slope is something like this? Yeah, we're current limited. We can swing through the full voltage range, but we can't swing through the full current range. So they call this current limited. Here, our actual load resistance is greater than the optimum termination resistance. Okay, now if we have RL being greater than our opt, the gain of the transistor is still more or less GM times RL, so we'll get more gain. We'll get lower saturated output power. That's kind of an example, talking about the difference between power transfer, power gain, and output power. Here, we're going to get more gain, but it will still result in lower saturated power. All right, now our other case here, what if instead of RL being too big, we do this? And you'll notice I tried not to move the quiescent point in any case. The quiescent point's the same. We've just changed the slope of the line. Sure.
Say our load, you mean before the matching network or after the matching?
This is what we're presenting to the transistor. Yeah. So I guess what I should say, I think when I drew this curve, I called this RL. What I should have done here, I'll change it in the notes now just to make it. This is because I drew that optimally. This is R opt. What we want to do is make RL equal R opt. The slope is, or the line is minus 1 over. The slope of the line is minus 1 over. Yeah. Okay. So that last case that I just drew, now the slope is steep. This implies that the load is less than R opt. And, obviously, opposite of current limited, we're going to be voltage limited. We can swing through the full range of current, but not the full range of voltage.
Can't you swing more than the full range of current, so you would blow up? Or like in the previous case, you swing past VD max? Is that a big concern?
You can do things that terminate. So we can terminate the device with other loads that cause higher current swings. So for instance, if I just put a short circuit onto the device, that would do that. But with a real physical resistor, it's probably not going to happen. But yeah, what this is showing ultimately is now my current swing can go even beyond the max current. Yeah. Yeah. And if I do that for too long, I'll heat the device up and blow it up. Yes.
Got like 20 seconds left.
20 seconds left. Okay. We will pick up here on Wednesday, and I will definitely incorporate a few lessons on doing some simulations, and I'll try and get a video or two uploaded as well, just so that you can start moving forward with your LNA examples. All right. So we'll stop there. Back with PAs on Wednesday and some simulation examples. VNE is, we sometimes call that the saturation voltage. Yeah.
So knee means high saturation.
We can call it that. I normally don't see it labeled that, but it could be. Yeah.
maximum range of the voltage, so the V to V max or VD max. do we have the maximum power gain or it is not?
Sorry, say that again.
So I'm just asking about the power gain, not the gain.
Yeah.
The power gain would be maximum when you're operating in the maximum swing of the drain voltage or the range.
No, the power gain, I mean, so GM times R is a voltage gain, but if we're a common source amplifier, we assume that that's proportional to the power gain, at least. So we're saying right now that power gain and voltage gain are synonymous with one another.
We just talk about the CMOS, not about the BJT or other.
Even with other amplifiers, it's the same phenomena that's going on, right? Yeah.
Are you saying power generated is more important than power gain?
Well, in a power amplifier, we ultimately care about power generated.
Right. Because, like, otherwise you just.
We do still care about power gain because our efficiency will be bad if we don't have good gain. So we do care about it, right?
Yeah.
But it's not, it's a secondary characteristic. If you have a certain power that you have to achieve for your transmit system to be able to close the link. So, in the end, I need to close the link between me and you. I do the calculation and that says the power to close the link is X. I have to hit that power.
Yeah.
If I don't hit that power, we don't close the link.
Yeah.
Yeah.
Okay. But is it true that the one with the steeper load line would be a higher power gain?
The one with the steeper slope, no, that RL would be less than ROPT in that particular case.
But when like a small BTS is causing a larger variation of the drain current, I'm thinking too much low frequency analog, right?
It's a little bit hard to think about, but the bottom line is that I might get more. In this case, I'm going to get maybe lower voltage gain, but more current gain. So I might get higher power gain. It's hard
Okay.
higher power gain.
Can't think of
So I might get higher gain, but I'm definitely going to get lower output power.
Okay.
Yeah.
On Wednesday, the LNA that's due, that